Hello everybody, and welcome to exercise 3 on page 148 of the workbook. Let's read this example together that they're asking us to do. So they're giving us a vector field, and they'd like us to calculate the flux of the vector field through a surface S, and they're describing the surface to us. Notice that the surface consists of two pieces. It's the region above the cone, z equals the square root of x squared plus y squared, and below the plane, z equals 1. Okay, and kind of a clue in the wording that indicates that we could use the divergence theorem if we wanted to. S is the surface of a solid region. That's the hypothesis, the situation that we need to use the divergence theorem. So we have a choice here. We could do this directly and calculate the flux directly, but it would mean calculating the flux through two separate surfaces. Or we could use the divergence theorem, which means we could break it down to one triple integral. Which choice would you pick? Well, probably doing one triple integral is going to be better than doing two separate flux integrals. So let's try the divergence theorem on this one. Okay, and when the divergence theorem is involved, there is going to be a solid interior of our surface that we're going to be integrating over. So let's give it a name and call it W. Okay, and then we'll go ahead and state what the divergence theorem says. So by the divergence theorem, the integral that we're trying to calculate, this flux integral, is going to be the integral over W of the divergence of f. Okay, and just a reminder again, what we're integrating over, W is the triple integral over the solid region. We'll keep that in mind as we're going through the problem. So we need to calculate the divergence of this vector field that we're given. That involves just taking partial derivatives of our three components, and if you do that, you're going to get 3x squared plus 3y squared plus 3z squared for your divergence. So let's go ahead and write that down. Okay, and since this is a triple integral that we're doing, we're going to need to set up limits for this integral. And anytime you do a triple integral, it's good to have a picture to be able to see what it is that you're integrating over. Okay, so they said it's the region above the cone. So let's draw the cone first. And below the plane, z equals 1. So if we label these, here's the cone down here. Okay, and up here, the kind of the flat top, the chopped off cone is going to be z equals 1. Okay, let's go ahead and put some axes in here too. So if we put in the coordinate axes x, y, and z, they'd kind of look like that. Okay, we want to set up a triple integral over this solid region W that we've just drawn. Okay, so what coordinate system should we use here? We need to choose a coordinate system. Okay, well, we've got choices, but one clue as to what a nice coordinate system might be is this x squared plus y squared here. In cylindrical coordinates, x squared plus y squared is equal to r squared. And so if we rewrite this in cylindrical coordinates, z would equal r. That's the equation of our cone in cylindrical coordinates. Okay, so if we make that choice to do this in cylindrical coordinates, generally you integrate in the z direction first when you do that. So let's ask ourselves what the lower and the upper surface are of our region. That's going to tell us what our limits are on the innermost integral. Okay, so the lower surface we can see from the picture is the cone, z equals r, and the upper surface, okay, the top is that flat plane z equals 1. Okay, so r to 1, those are going to be the limits of the innermost triple integral that we're about to set up. Okay, and then we're done with the z direction, so we need to project. Okay, so this is where we imagine shining a light down on this region W straight down the z-axis, and we'd ask what shadow would we see down in the xy plane. Okay, well, you've done this sort of thing before in previous chapters. What you're going to see is the widest part of your region, okay, this curve of intersection, this circle between the cone and the plane. Okay, so over here in the xy plane, that's going to kind of look like this. Okay, but the question is, how big is that circle? Okay, in order to figure out the rest of our limits of integration, we need to know what the radius of that circle is. Okay, so here's where we can use the fact that we noticed that that circle is really the curve of intersection between these two surfaces. All right, so let's do a little side calculation down here. Okay, where we ask what that curve of intersection is. It's what we get if we take the lower and the upper surface and set them equal to each other. So if z equals 1 and z equals r, and set those equal to each other, we get r equals 1 as the intersection curve, and that tells us that the radius of this circle over here is 1. Okay, so we have enough information now to write down all the limits on this triple integral. So we're going to draw a big arrow here and continue the calculation that we started above. Okay, so let's see if I can get both of these in the picture here. So let's rewrite that integral. We're about to write this as an iterated integral and write down our limits. One thing we can do to make things a little easier on ourselves is to notice that 3x squared plus 3y squared, we can simplify that by pulling out a 3, and then notice that x squared plus y squared is r squared. Okay, so here's our three integrals. We're going to have a 3r squared plus a 3z squared. We already mentioned that we're going to integrate in the z direction first, so the dv element is r dz d theta dr in cylindrical coordinates. And our limits, again on the innermost integral, are sitting there, r to 1, so we'll put those in first. Okay, and what about the theta and the r limits? Well, they're going to come from our projection picture over here. That's a perfect circle that we're integrating over, so we're going all the way around, which means that our theta limits are 0 to 2 pi. And what about the r limits? Well, we can see from the picture that the radius of the circle is 1, so that's going to go from 0 to 1. Okay, there's the triple integral that we need to do to finish our problem here. All right, so let's take this in stages. So, maybe just to make this a little bit easier, before we do any integration, we could take that r and multiply it through. That's going to give us a 3r cubed plus a 3z squared r. Okay, and we want to integrate that with respect to z. Okay, so this first term is going to turn into a 3r cubed z. 3r cubed is constant with respect to z. And then if we integrate the 3z squared r, that 3z squared is going to integrate to z cubed times r. Okay, and then we have to plug in our z limits, which are 1 and r, and we've still got a d theta dr to take care of. Okay. So, moving to the next step here, let's see. Still got an integral from 0 to 1 and 0 to 2 pi. Go ahead and substitute in our z limit, starting with 1. So if we plug that in for all of our z's, we're going to get a 3r cubed plus a, going in for z. So 3r cubed plus 1 cubed times r is just r. There's our upper limit. And if we plug in r for all of our z's, we're going to get, let's see, a 3r cubed times r is a 3r to the 4th, plus an r cubed times r is an r to the 4th. Okay, so far we've got that. Okay, now notice a couple of things here. So first of all, we're getting ready to integrate with respect to theta, but our function doesn't have any thetas in it. So what's going to happen when we do that integral? Well, we're going to integrate d theta, and we're going to get a theta, and it's going to be evaluated between 0 and 2 pi. That's going to give us 2 pi minus 0. In other words, that integral is just going to give us a constant of 2 pi, which we can pull outside. I'm going to do that in one step. Okay, and what's left is just the part that's on the inside here. Okay, Okay, then it would be practical just to do a little simplifying here. So if you combine like terms inside of that integral, here's what you're going to get. So we're going to get, let's see, a 3r cubed plus an r. Put those r to the fourths together into a 4r to the fourth. And at this step, we've really reduced this down to just an ordinary calculus 1 integral. There's just one variable in there. I'm trusting that you can do that kind of an integral by now. And if you do that and work through the details, you should come up with 9 pi over 10. You can just double check and make sure that that's correct. All right, and that is our answer.